This video is going to go over section 5.4 called conditional probabilities. So conditional probability is the probability that one event happens given that another event is known to happen. So they give you two different formulas. So the probability of B given A is written as probability of B and then a vertical line A. So the vertical line represents the given. Okay, so when you see that, that means given. Is the probability of the intersection of A and B, so that's the and, so where A and B are both true, divided by the probability of A. The way that I remember it is that the A comes last, right? So that's going to be the denominator value. Notice then that the probability of A given B has the same numerator, but then the denominator is the probability B occurs because it was last. Okay, so these are the two formulas for the probability of A given B and B given A. So make sure that you have those in your notes so that you can apply them when you have to calculate a value. So these formulas we actually used in the first chapter, they just didn't give them to you. So I know a lot of people struggled with this at the beginning, so hopefully that makes this easier because you've seen it before. When we talked about two-way tables. So a researcher randomly selected 158 personal vehicles and noted the type of vehicle and its color. The two-way table displays the data. Suppose a vehicle is randomly selected. Let the event C equal convertible and R equal red. What is the value of the probability of red given convertible? Okay. So ultimately, what we're looking for then is, the probability of red and convertible divided by the probability of a convertible, okay? And so I'm gonna kind of go through two ways to do this and we'll see why we can use both of them. So the probability that something's both red and a convertible is 20. There are 20 red convertibles over 158. Divided by the probability something is just a convertible. So the convertibles, there are 29 of them over 158. So what I can do when I have a fraction like this is that if my numerators are the same or if my denominators are the same, I can reduce them. So that means that I can reduce those values instead of having to calculate the values. So then I could do 20 over 29. And then if I calculate that as a decimal, that's going to give me about 0.69 or 69%. Okay. So when we talked about given the very first time, I talked about, okay, whatever's after the word given, so in this case, whatever's after the line, that's the only row or column I'm interested in. Okay, so then my numerator was the red ones from that row. So 20 red divided by the total is what we ended up with. So that's the shortcut that you can use to find these values for a given problem. There are questions that will ask you to like interpret your solution. So what that means is that there is a 69% chance a red vehicle is chosen. Wow. Yeah. That looks weird. Maybe just because my C looks like an E. Is chosen given it is a convertible. Okay, so the probability of R given C in words is that equals 69%, is that there is a 69% chance a red vehicle is chosen given it's a convertible, right? I know a convertible was chosen. There's a 69% chance that that convertible is red. In the next question, we don't have a two-way table, but we do have probabilities. So a recent survey found that 65% of high school students were currently enrolled in a math class. So that means the probability that someone is taking a math class is 65%. 43%, sorry, which written as a decimal is 0.65. 43% were currently enrolled in science. So the probability choosing someone that has a science class is 0.43. And 43% were enrolled in both a math and a science. So the probability that someone is in a math and a science class is 0.13. Suppose a high school student who is enrolled in a math class is selected at random. So that means that we're given the math class. What is the probability that the student is also enrolled in a science class? So what this question is asking us is, what is the probability that a student is enrolled in a science class given we know they're already enrolled in a math class? So remember that if we think back to the formulas, the way that this works is that this one is going to be the denominator probability. So the probability of math is going to be in our denominator. The numerator is always, every single time, the intersection. So the intersection of math and science. So the numerator is who's taking both math and science classes because it was given a math. Our denominator is going to be the probability for math. Okay, so the probability someone is in math and science was 0.13 divided by the probability that someone was taking a math class is 0.65. And so if we divide those two values, we get 0.2, which is also 20%. So depending on what your options look like, the probability is 0.2 or 20%. Okay, one more example using these conditional probabilities. So example says that a random sample of adults was asked about their highest education level completed. The distribution of results is shown in the table. What is the probability that the highest level of education of an adult is a high school diploma, given that they have completed at least one of the educational levels shown? So they want the probability of high school given at least one of high school, trade school, bachelor's degree, and master's degree. None completed would not be completing an education level shown, right? So what we're looking at then is the intersection of high school and all of these, right? So high school is part of it. So that means that the high school diploma percentage is 0.03. The denominator is going to be the probability that they got one of these, okay? So they had one of those. There's two different ways we can do this. The whole table should add to 1. So we can either do 1 minus the one we're not counting, 0.16, or we can add up everything, 0.03 plus 0.44 plus all the way through. Either way, we should get 0.84. Okay, so the probability that someone completed at least one of those, high school, trade school, bachelor's degree, master's degree, is our denominator. So if we divide these two, we're going to have to get an approximation. We get 0.0 and then it's 3.5, so that's going to round up to a 4. So 0.04, or if it's written as a percentage, that would be 4%. Okay, so the last topic here is whether events are independent. And so independent events rely on conditional probabilities. So knowing whether one event has occurred does not change the probability of the other event will happen, means that they're independent of one another. And so ultimately what we're going to use is part of this first one. So we're always going to check, does P, the probability of A occurring, is that the same as the probability of A occurring given B occurred already? So that's what we're going to check each time. If that is true, then yes, the events are independent. If that is not true, then no, the events are not independent. So they're giving us what events A and B are. So here's our two-way table of high school students categorized by grade level and music preference. So we have juniors and sophomores, whether they like listening to it in earbuds versus speakers. So suppose a high school student is selected at random. Let the event A equal junior and B equal earbuds. Are events A and B independent? So in order to check this, we want to find the probability of event A. So the probability that a student is a junior. So that would mean that I'm taking all the juniors, which is 16, divided by the total for the sample space, which is 32. So if I divide 16 by 32, that's half of the students. Okay, that's 0.5. I'm going to compare that to the probability that a student is a junior given they prefer earbuds. Okay, so remember the way that this works is that if I'm given they prefer earbuds, I'm only concerned with numbers in the earbuds section. Okay, and so the numerator is where junior and earbuds meet. So the numerator is 4. And then the denominator is the total for earbuds. So there are 8 students that prefer earbuds to speakers. This value is also 0.5. So what this means is that yes, these events are independent because P of A is equal to P of A given B. Oops, I don't want to cross those off. I guess it doesn't matter. Okay, let's look at one more just to make sure we understand that concept. A researcher randomly selects 158 personal vehicles. Note the type of vehicle and its color. So this is the same two-way table from the beginning. So suppose a vehicle is randomly selected. Let the event A be that that car is a convertible. So the probability of A is going to be 29. Oops, I should have changed colors, sorry. Come on. Guess not. We're just gonna use black. 29 over 158, which if I calculate that is going to give me about 0.18. And then we want to check, is that the same as the probability of A given B? So if I'm talking about A given B, I'm looking at, B is red, so I'm looking at this information only. I'm ignoring the rest of the table. So there are 20 red convertibles out of 43 red cars, which gives us a value of about 0.47. Since 0.47 and 0.18 are not the same, these events are not independent because the probability of A is not equal to the probability of A given B. Okay, so independent events happen when the probability of A is equal to the probability of A given B. And then we use the formulas. Probability of A given B is the probability of A and B both occurring at the same time, divided by the probability of what was given, so the probability of B in that case.